Come on in. Feel free to ask questions if you have them. Hey, various. I already mentioned this to Sang and John, but I just let you know you're welcome to ask questions while we're waiting for everybody else to get here. Class doesn't start for another 5 minutes, but I'm here. Just waiting for everybody to show up. Now I'm grooming. Finally got hair, but it's on my face as opposed to my head. That's disappointing. Let me test to make sure my ability to share screen is working. Share screen. Okay. Lisa's working on to download anything. Still got 2 minutes for class, so feel free to ask any questions you might have. Luckily, my wife fixed me some tea and I can kick back and enjoy it. She actually offered and never showed up with it, so I was just picking on her. Obviously, it's not her place. She is my bride and doesn't owe me a damn thing. But she's sweet and she likes to do stuff like that for me. Thank you, baby. It was delicious, that tea was. Come on in, everyone. Nice to see you. So we lost 2 greats over the weekend. Really a bummer. We lost Jimmy Buffett, and we lost the lead singer of Smash Mouth, Randy Newell, I think his name was. And this morning I got up and John Goodman was trending on Twitter, and that freaked me out. Evidently, that freaked out everybody. So there was a big hoopla on Twitter, and he is fine. I think the hoopla was about him doing a voiceover for a character. I think Mario or something like that. But anyways, he's alive. Everything's good. He was the guy that played Roseanne's husband on the Roseanne Barr show, but he also did Sully's voice on Monsters Inc. And he's the Big Lebowski, which is my favorite role. He also played Fred Flintstone in the Flintstone movie with Halle Berry. Oh, and evidently a jury has found Danny Masterson guilty of raping 2 women. That was horrible. I was really a big fan of his, and I hate to think that a jury that there was enough evidence that he had done something horrible like that. So a jury has convicted him, and he gets what he deserves, of course, if he really was guilty, which seems he was. So people that you like aren't necessarily what you know about them. All right. Well, it's 5:20, so we should go ahead and go. I've got 8 of you. I think there's only like 9 or 11 in the class, so this is plenty enough. Does anybody have any questions on any past material? We're well into chapter 19. I was suggesting we probably finish chapter 19, but just in case, I shifted the dates. I think the date of the conceptual questions for chapter 19 is now the 13th, as well as the date for the first set of the homeworks is September 13th. And then from there, I think it's the 18th for part 2. You should have no problem meeting that, but I would definitely try to do it ASAP. I think I sent an email out yesterday about test 1 and test 2, and then I looked, and evidently I had an old version of the lab schedule, and it made me think that next week's lab series would be when we're taking the test 2 face-to-face, but I was wrong about that. It seems to be the week after, and if you're a Monday lab, it's like almost 3 weeks later. So just to let you know, week 2 or the first face-to-face test will not occur for about 2 weeks at least. So just keep that in mind. Well, actually, I shouldn't say at least. It's about 2 weeks. Okay. And because of that, we might actually fit in 2 online tests before then as opposed to 1. So right now we have 1, and I've got a practice test up, and I've got the online test up as well. I think I made the due date the 12th of that. So make sure y'all get that done. You get up to 3 attempts, and only your highest counts. Remember, it's open notes, open book. The only thing that really is cheating with the online tests for me, because I count them so low and all that good stuff, but the only thing that's really considered cheating is any way in which someone could take the test and then communicate or help you with what they've seen. So if they didn't talk about anything they saw on there, you can talk to them all day long. That's not a big deal. But if they talk about anything that was on that test or give you hints on how to do any of those things that they know were on the test, then that is cheating. So just avoid that. Don't let them do it by any means, either by making notes after they took the test and then letting you look at the notes, or by making a website that has notes about the test, but not necessarily even call it the test, but was actually notes from the test. So don't do any of that stuff. As long as you don't do that, then you're not cheating. And generally speaking, students get really good grades on these. So that should help your grade anyways. All right.
So this test is going to be on the 20th?
Let's look at a calendar.
In person?
The in-person one looks to me, let's see if I even have that. Let me pull open my folder and see if I have that schedule here. I think I might, but I'm not sure if I do.
I gotcha. And then the in-person test is also going to be just like an online test, but just in person instead, correct?
It's not just like an online test. It's basically more like a regular test. So it might be on Canvas, in which case you'll use a computer and all that stuff, but you're not allowed to surf the web. You're not allowed to use notes. The only thing you're allowed to have is a scientific calculator and equation sheet. And as far as the equations go, you're only allowed the equations that are in your textbook and are numbered. So when you look in your textbook, for instance, I'm looking at an equation right now in your textbook. Okay, I thought I was going to be looking at an equation right now in your textbook, but a typical equation would have a parenthesis and then a 19-2 close parenthesis. If it has a number like that, then it is acceptable as an equation for your equation sheet. What I would do is start on, I think we started with chapter 17. So I go through 17 and write down every equation that has a number by it, or at least the ones that you've used in doing the homeworks and the practice tests, and then do the same thing for chapter 18, then do the same thing for chapter 19, and just keep that for the whole semester, because you can use it for all the face-to-face tests. I'm hoping to have one for you, but until then you have that, and you can be assured you at least have as much as what you made up by doing it the way I just said.
Okay, and then this in-person test is going to be on 19 and 20, chapters 19 and 20?
No, that's test 1, which is already open, and that's the online test. That's 19 and 20. Then excuse me,
be 17
test
18,
1
right?
was 17 and 18. Test 2 was 19 and 20. So test 2 might be an online test on 19 and 20, and then the first face-to-face test might in fact be on 17 through 21 or something like that. It could be like that, or it could be just a separate one on 21 and 22 or something. It all depends on how much we cover and that sort of thing. Does that make sense?
So, I mean, yeah, but I was just wondering what this test is going to be on so I can actually prepare for it.
Okay, so that's the good news is test 1, the practice test you've been doing for that is helping you for test 1, which is already posted and online. Then when you finish that, you're going to start doing online practice tests for test 2, which is going to cover 17, 18, 19, and 20. If if the time plays out right, that could be what your third test will be on the face-to-face test, or it might be that it's on the next one. But either way, you'll be practicing for it. So you'll know more than a week in advance. And I just pulled up the schedule, and basically it'll be between the 19th and 25th, whichever one of those days your lab is on. Your lab meets on Tuesdays, right? So that looks like
Yes,
it's
sir.
19th.
Okay, perfect.
Yeah. Next
then
week
you
you'll have a
said it
better
would,
idea what it's on.
okay, all right.
Okay. What was your other
So
question?
you're not
I spoke
100%
of you.
sure if it's 16 and 17 or 17 and 18 or if it's 19 and 20 yet?
Yeah, we'll know that. We'll definitely know that next week. I'll make sure I tell you about the 12th, or you can ask me again on the 12th, because that'll give you a whole week. I'll have had the practice test made up and all that. It might, like I said, it might just end up being a regular test too, which would be another version of the chapters, which are technically 19 and 20, but it includes 17 and 18. So it could just be that, or it could be 17, 18, 19, and 20, and 21. So I'll know that by the 12th.
Okay.
Okay, so that'll give you a whole week, in other words. Anyone else? All right, well, when we last spoke, I did show you that diagram, and I'm referring to the diagram about latent heat that you see on figure 19.5 in your textbook, which is in section 19.5. It was that diagram where we had temperature on the vertical axis and heat added in kilocalories on the horizontal axis. And it was basically the process and the temperatures that a single kilogram of water starting off at negative 40 degrees Celsius would actually go through, and going from negative 40 degrees Celsius to 0, turning into water, and then to 100, turning into steam, and then up to 130 roughly. So that's what we did somewhat last time. So now I'm going to go with that, and using, for instance, the data table that's listed in table 19.2, we're going to solve a problem with latent heats. So I've got it written down. Let me go ahead and share my screen with you guys. Share screen. And of course, these notes are always available on Google Docs. So if you're in my class, obviously you already have access to it. Of course, if you're online and you want access to it, you just send me an email and tell me what episode you're interested in specifically. There's a string of letters in the comment section or in the description section that say PHY242, and then it has like a date after it. If you give me that information, I can immediately tell you exactly which one it is and send it to you. So anyways, that's just to anybody's on the web. I've got some students that are taking like 201 or 202 right now that are actually watching my 241 and 242 videos because they're taking the calculus base next, and they think they can do a little better if they've already had some exposure to it. So that's why I'm saying that. All right, so here's the problem. It says a 0.750 kilogram block of ice has a temperature of negative 15 degrees Celsius when it is put into a cooler that contains 3.50 kilograms of water at 21 degrees Celsius. What will be the final temperature? And I'm going to ask, excuse me, I'm going to ask questions about the phase, or at least I'm going to tell you about the phase. So what we've learned is that the specific heat of water is really high. Ice, on the other hand, has a specific heat that's half as much. So, for instance, the specific heat of water is 1 calorie per gram Celsius degree Celsius, or Celsius degree, whereas the specific heat of ice is 0.5, and the specific heat of steam is 0.48. So you can see that water is really a big deal in terms of being a good insulator. So if you put a fairly small quantity of ice, 0.750 kilograms, which is about a fourth as much as the water is, into a water cooler, then the temperature is going to get a lot closer to the temperature of the water as opposed to the temperature of the ice. So what we should suspect is that we're going to actually throw this ice in the cooler. We're going to assume that all the heat is lost just between the ice and the water, so that none's going out to the environment. That's why I'll put it in the cooler. And in doing so, we're going to work out what that final temperature is. But based on our knowledge of water, what we suspect is going to happen is that the heat in the water will be sufficient to, one, bring the ice temperature up to 0 degrees Celsius, and two, then provide the latent heat of fusion that's necessary to finally melt the ice. And then the whole thing should be in a liquid state. Now, when we calculate that, if we come up with a temperature that's lower than 0 degrees Celsius, then we'll know we've made a mistake. Your book actually does a problem very much like this, and it gives you two different ways of solving it. And I highly recommend you look at my version and my description, and then look at his two versions, and I think you'll find it pretty helpful. So let's start off with our solution. What we're going to use is basically three equations. You can use the delta Q equals 0, which is what a lot of authors use. I don't care for it that much because I often remember when I was taking the algebra-based course, I would get confused sometimes in the excitement of a test, knowing whether latent heat was positive or negative when you're going one way versus the other. So I came up with this way, which is Q lost, and it literally changes names every time I write it just about. So Q lost equals Q gained. What I mean by that is there's some items in the system that are losing heat, and then there's some items in the system that are gaining heat. So I take all the heat that's lost from the items, add them up, and then I take all the heat that's gained from the other items and add them up and set them equal to each other. And that's equivalent to delta Q equals 0. But by doing it this way, I make sure all the signs are positive, and I have to throw away the idea that a delta means final minus initial, because in this way, when I'm doing it, Q lost equals Q gained, I have to have a positive change in temperature. Everything's got to be positive. So that's one of the equations I'm using. Another equation I'm using is that heat is equal to MC delta T, where that's the heat added to change the temperature of a mass M of a substance that has a specific heat C by an amount delta T. And then one more is Q is equal to M times L. And that L can be subscripted with a F or a S or a V, meaning fusion or sublimation or vaporization, stuff like that. So let's start off. What we know is losing heat is in fact the water. Well, you could, in fact, a lot of times we'll call this, we'll say we're working with tea or something like that. And I'll just warn you that there is a little bit of danger. If you put too much stuff in tea, it's no longer that much like water. So it can change the density, it can change the specific heat and all that sort of stuff. So just be careful with that, or at least state it when you're trying to actually apply it to real physical problems. If we can assume that the specific heat of tea is the same as that of water, then blah, blah, blah. But in this case, I just said it's water, so it took that problem out of it. You'll see in your book, they actually did, as I said, a similar example, but they were using tea. So the thing losing heat, like I said, is the actual water. So what we get for that is the water is going to change temperature, and the water has a mass of 3.50 kilograms. So I'm going to say supposed to be back in black. Supposed to be 3.50 kilograms times C, which in this case, since it's in kilograms, I'm going to use 4,186 joules per kilogram Celsius degree. And remember that Celsius degree means it's supposed to be multiplied by a difference in temperatures. Now, the water is actually going to go from 21 degrees Celsius to something colder. So final minus initial would give me a negative. I don't want that. So I'm going to say 21.0 degrees Celsius minus T instead. So that makes sure that it's positive, in other words. Now, that's all the heat that's going to be lost, because it's really just the water that's losing it. And the water is not going to change state unless we find that we get a temperature that's negative. Or even close to 0, we might find some weirdness going on there. But basically, as long as that's not the case, we're golden. So now I'm going to say Q gained is the actual ice block, and its mass is 0.750 kilograms. Its specific heat is actually 4,186 divided by 2, roughly. And I'm using more sig figs than is really reasonable. But 4,186 divided by 2. I did this on the fly when I did it in my class, and I got it right, but I just want to be careful. So it's 2,093 roughly. I think your book is going to use like 2,100 for that, and that's roughly what it is, because we usually don't have more than 2 or 3 sig figs. but 2093 joules per kilogram Celsius degree. And now the ice is going to go from -15 to some higher temperature. So I'm going to do temperature minus -15.0 degrees Celsius for that one. That way I know it's going to be a positive difference. So T minus -15 becomes T plus 15. So it's got to be positive. And then plus, because not only am I going to change the temperature of the ice from -15 up to 0, I'm going to actually then cause the ice to change state. And that's just if I get up to a temperature of 0 and then melt it all. So I have the Q equals ML formula, that'd be 0.750 kilograms. And looking at table 19.2, I see the heat of fusion for ice, or for water, because remember, it's the same element, so you just use water. That one actually happens to be 3.33 times 10 to the 5th joules per kilogram. Notice that just has joules per kilogram, not joules per kilogram Celsius degree. Now that just brings it up to 0 degrees Celsius and then melts all the ice. So now I need the ice in water form to be raised up to that same common temperature. So now I have another term that's 0.750 kilograms times 4,186 joules per kilogram Celsius degree. And then again, we're going to bring the temperature up from 0 to some higher temperature. So the T, the final temperature, will be higher than 0. So I'm going to say T minus 0.0 degrees Celsius. So that should be all of it. Now, as long as this temperature comes up to be greater than 0, then everything I've set up is correct. If not, I'd have to consider other things. And there's other ways you could do this. You could just sort of think about how much energy does it take to bring the T down from 21 degrees Celsius to 0, and then compare that to how much energy it takes to bring the ice to 0 degrees. If the first one's bigger than that, then you can say also how much it's going to take to melt it. So you add that term, and if it's still bigger than that, then you know that you're in the right track. So anyways, let's go ahead and do all this. I'll suspend units for a little bit just because they get messy, but I will sort of state them without writing them. So 3.5 times 4,186 times 21 is going to give me 3.07. I'm going to carry one extra sig fig, so 3.077 times 10 to the 5th. Now, in this case, that was kilograms times joules per kilogram Celsius degree times Celsius degrees Celsius. So really what that ultimately gives you is just plain joules, but I'm going to leave that off. Now I'm going to do the same thing, the 3.50 times 4,186. And then that's just times T. So this will be minus 1.470 times 10 to the 4th times T. And that would actually be joules per Celsius degree, would be the units of that parenthetical. So that's the whole left-hand side. The right-hand side is going to be 0.75 times 2093 times T. That gives me 1.570. Again, one extra sig fig there. 1.570 times 10 to the 3rd. Now that one is actually, let me make that a little clearer. I just screwed up that 3. So 1.570 times 10 to the 3rd. That one times T is going to be basically joules per Celsius degree in the parentheses, and then times T. And now I'm going to do 0.750 times 2093 times 15. And that one comes out to just joules. But again, I'm not writing the units. So this one's going to be a plus because it's minus a minus, and I get 2.355. Actually, since that's a 4.6, I should really, this is kind of a pain in the butt. 2.3546. I'll carry 2 extra sig figs, in other words. And weirdly, that's times 10 to the 4th. And that's the actual joule one. Now I also need, that was the second term of basically the first term because there was a subtraction in it. So now I need the one for the M times L. So I'm going to do 0.750 times 3.33 e to the 5. That gives me 2.498 times 10 to the 5th. And that one comes out to just be joules because it's joules per kilograms times kilograms. So that's the ML term. And now I've got to do 2 more terms. Luckily, one of them is a 0. So multiplying by 0 is just going to give you 0. So I only have to write out one of them. But it's 0.750 times 4186 times T. That gives me 3 plus 3.13. Actually 140 to 1 extra sig fig. 140 times 10 to the 3rd. And that one's actually multiplied by T. So the units actually came out to be joules per Celsius degree in the parentheses times T. So what I'm going to do is I'm going to try to get all the T's on one side and all the non-T terms on the other side. So I'm going to add that 0.1470 times 10 to the 4th. I'm going to add that on the right-hand side. So I'm going to say 1.47 e to the 4th plus 1.57 e to the 3rd. So that takes care of, let me mark this off. That took care of that term and that term. And now I say plus 3.14 e to the 3rd. That takes care of that term. And that gives me equals 1.941 times 10 to the 4th times temperature. So that took care of all those terms. Now I'm going to take that 3.077 e to the 5th, and I'm going to pull the 2.3546 to the other side, which is going to make it be subtraction. So I'm going to say minus 2.3546 e to the 4. That takes care of this term and this term. Now I've got to take the minus 0.249 or 2.498. So I'll say minus 2.498 e to the 5th. So that took care of this term. Notice I'm marking it with a different symbol. And that's actually it. So the left-hand side becomes 3.435. Oops. 3.435 times 10 to the 4th. Now I can put the units in. That's going to be joules. And this side over here is going to be, I'll write in like this. That's going to be joules per Celsius degree. So now I can find that the temperature is going to be that 3.435 times 10 to the 4th divided by 1.94. And that gives me something I did not expect. I'm suspecting there might be an error in here because I got 5 degrees the last time I worked it. So there's probably some arithmetic error. But what I got was 3.435 times 10 to the 4th joules over and that 5 is not a sig fig, by the way, divided by 1.941 times 10 to the 4th joules per Celsius degree is equal to 1.7699. Actually, that degrees Celsius is equal to T. That's what I got, but as I told you, I think. Oh, no, that's right. That's right. No, and this should be good. I don't see any reason for a mistake here. I was remembering the answer, but that was when I actually did the problem in the book. This one's been changed quite a bit from the one in the book. I just sort of made this up on the fly, and it's got much different numbers. So that's probably not unreasonable. So what I'm going to say is the answer to this is T is equal to 1.77 degrees Celsius. And I suspect that's right. Does anybody have any questions with that? When I made it up, I tried to make it come closer so it just barely get over melting the ice. So that's why I ended up using like 3.5 kilograms of water and basically made the temperature a little bit higher than the examples that I'd already worked. So does anybody have any questions on that? All right, let me turn on the comments, the chat, so I can see in case anybody's writing anything. So I'll put that there. That all looks good. Now, with that in mind, we've basically covered all the major stuff regarding calorimetry. So you can compute stuff like this and just use it to solve calorimetry problems. Your book has a little box called problem solving on calorimetry. I definitely recommend you reading that. But the rest of it's pretty straightforward. It's just more of this. You can see plenty of examples in your book. You have enough to go on for this type of problem in chapter 19. So we've now covered the heat and the first law of thermodynamics and the difference between heat and temperature and that kind of stuff. And internal energy, that's the three things they differentiated. So remember that it really is the temperature of two bodies that dictates whether heat will flow. So if you put two bodies against each other, if they have different temperatures, then the one with the higher temperature is going to allow heat to flow from it into the one of the lower temperature. And that doesn't matter whether the hotter one has a higher internal energy than the lower one or not. It doesn't matter at all. And that should make sense, right? Because if you jump into a pond or a lake or the ocean, the pond, the lake, or the ocean are all colder temperatures than your 98.6 body temperature. So you know heat is going to flow from your body into the water. And you know that because even when people fall over, say from a cruise ship in the Caribbean or something like that, they still have the danger of hypothermia. So you know heat's flowing from the human body into the body of water, which if you talk about the ocean is obvious that the internal energy is way higher than the internal energy of the human. So that's what that is. And the heat is really the flow of energy from one object to another. And the kinetic theory, the way we picture it is, which is basically using the atomic or molecular theory of matter, specifically when you put a temperature, an object of a higher temperature against an object of a lower temperature, the atoms and molecules in the object of the higher temperature have a higher average kinetic energy because that's the definition of temperature. And those atoms and molecules are sort of like playing bumper cars with, matchbox cars versus, let's say, actual cars. Okay, because the kinetic energies of actual cars is much bigger than matchbox cars. So what's going to happen is those actual cars are going to ram into those matchbox cars and cause them to speed up. And that speeding up is not necessarily an increase in temperature, but once that overall equilibrates so that the net kinetic energy of all the matchbox cars is about the same as the net kinetic energy of all the real cars, then they'll have reached the final temperature or the final equilibrium temperature. And that temperature, of course, will be somewhere between those two bodies. So the cars, of course, they're going to lose some kinetic energy by their collisions, and the Matchbox cars are going to gain some kinetic energy. And once the total kinetic energy of the Matchbox cars equals the total kinetic energy on average again of the real cars, then they're in what's said to be equilibrium and no heat flows anymore. So that's how conduction works. There's also convection and there's also radiation, and we'll give you those laws dictating how those behave as well. That's part of this chapter. But right now, what I want to go into is we've done latent heat. I've mentioned a bomb calorimeter before, but basically they have those at, for instance, Virginia Tech. A friend of mine makes hot sauce, and he sent his hot sauce there, and they actually will literally put the food that you send them in a bomb calorimeter, and that'll detect how many calories it is. And that's how you determine the calorie content of a food. So that's what they mean by a bomb calorimeter. Your book talks about evaporation as well, which basically when you sweat, your body is releasing some of the water, and the water is more or less at body temperature. So it comes out, and then that water can actually be cooled down a little bit from the air rushing by it. And that cooling of the water then cools your body. But the major effect of it is when basically it gets to the point where the sweat actually evaporates. And when the sweat evaporates, it takes the gases, which are not in a lattice, it takes the molecules, which are not in a lattice, but they're still in that liquid form where there's a certain long period of time, at least on a microscopic scale, a long period of time where one particular atom or molecule is spending all of its time with two or three very specific molecules. And that happens for, maybe it's on the order of microseconds. I'm not sure. But the main point is it's a long time for a microscopic level. Whereas if you look at a gas, the molecules are 1 second next to one molecule, and the next instant they're next to entirely different molecules. So you still have some bonding energy, and that latent heat being pumped in for evaporation is going to be able to break those bonds. So your body is actually taking some of the heat that it has and putting it into the sweat beads on your skin and causing those bonds to break. And that gives you yet another decrease in body temperature because you're losing some of your heat. So that's really how sweating works. And that's what evaporation is about. What we're going to go on now to is the kinetic theory of latent heats. And basically what we're going to do is I'm going to remind you that we learned about the molecular and atomic behavior of elements. And we use the kinetic theory, for instance, to derive the average kinetic energy of the molecules or atoms in an ideal gas. And what we're going to do now is say, let's recall that the internal energy for an ideal gas, it's actually a monatomic ideal gas, is 3/2 nRT. Or you could say it's 3/2 N times the Boltzmann constant times T. But this is for a monatomic ideal gas. Okay. And while we're doing a monatomic ideal gas here is what we sort of discovered. I didn't make a big deal out of it because it wasn't our goal in that derivation when I derived the kinetic energy. What we discovered is the motion in the left-right direction, say, either all of these three directions are arbitrary. I'm just using because that's normally what we do. But there's three independent perpendicular directions that exist in three-dimensional space. I'm using the representative quantity of left, right, in, out, up, down. Okay, so that's X, Y, Z. So there's three dimensions, period, and each one of those get a 1/2 kT for the kinetic energy in that particular direction. So it's like a 1/2 kT for each mode of motion in terms of kinetic energy. Now, if you take a single atom, that's the way it behaves. But when you start talking about molecules, then there's other degrees of freedom that it has. So a single molecule can move left, right, in, out, and up, down, and each of those get 1/2 kT of energy. However, if you go to just a diatomic gas, let's say like O2 or H2 or something like that, then you've got two atoms on the end of a bond. They act sort of like a dumbbell. Now that whole atom system, that molecule can have its center of mass move left, right. That gets 1/2 kT degree of freedom. It can move in, out. That gets another 1/2, and it can move up, down. That gets another 1/2. And those are the degrees of freedom that are associated with temperature. However, you can also take that molecule and you can rotate it this way. That gets 1/2 kT. And you can rotate it this way, that gets 1/2 kT. You can actually rotate it this way, but that's individual atoms rotating on their axis, so that's not a very appreciable amount of energy. So you only get 2 more degrees of freedom from that. But in bonding, they also have a degree of freedom like this as well. So I was once taught to think of it as all the something x squared energy terms you can come up with. And so far, what we've learned in class from the 241 and some bits of the 242 class is that you have a kinetic energy that's like 1/2 kx squared, but you have a rotational kinetic energy that's like 1/2 I omega squared. And then you have a springs potential energy, which is like 1/2 kx squared. And that 1/2 kx squared is the molecule vibrating like that. The 1/2 I omega squared, in one case, it's for rotating this way. So that's a particular I. And then it's rotating this way for another I. So that's why you get additionally 3 degrees of freedom. So in that case, you might say, if each one really got a 1/2 kT for the energy, in this case, the internal energy for a diatomic might be 6/2 nkt. Okay, so that's really what we're getting at with this. I'm going to move on from the kinetic theory of latent heat to the first law of thermodynamics. And the first law of thermodynamics specifically says that E internal, and I'll write it this way, delta E internal is equal to Q minus W. Now, if you've had chemistry, you might have had this first law of thermodynamics before, but in chemistry, they use Q plus W. Okay, so I need to make some explanations about that. This is the change in internal energy. And a lot of books call that U, by the way. We're sticking with E internal. And that means E internal final minus E internal initial, as delta is almost always supposed to mean. Like I said, that one case where Q lost equals Q gained is a case where you don't do final minus initial, but generally all the other times you do. This Q right here is heat added to the system. So whatever sample of gas or sample of water plus ice that you're looking at, when you put heat into that, that's a positive quantity Q. And this W right here is work done, and here's a key word, by the system. So when chemistry does plus W, that's because they are actually using work done on the system, and we're using work done by the system. Your book talks about that's a ramification of early steam engine thermodynamics, where the output really was how much work was it doing. So it just became natural to do that. Now, we can also write this sort of in a differential form, but I want to warn you a little bit about that. You could also say, we're going to call this the first law of thermodynamics. Actually, I'm going to try to write that so that you can see all the letters. So that's the first law of thermodynamics. And another way we can write that is dE internal is equal to, and your book makes a point to point this out as well. Notice I wrote a dE internal. That is a differential change in the internal energy. And it could literally mean like differentials, like in terms of calculus, because the internal energy is one thing you can treat as a state variable, or even a type of equation of state, if you will. However, Q and W are not state variables. So there's no way, for instance, that you can have initial conditions and final conditions and have matter just depend on Q in that way. So that's really why you can't say they're exact differentials. So what you're meaning by putting that bar on that is just saying it's a very small amount of heat added minus a very small amount of work done by. So that's the key thing. Again, when I say heat added to the system, I am referring to Q greater than 0. And when I say work done by the system, I'm saying work is greater than 0. Okay. And internal energy, we already knew what it was for an ideal monatomic gas. It appears, at least for an ideal monatomic gas, to only depend on the temperature. And if the internal energy increases, one way you could do that is by adding heat. And even if you locked it down so that no work could be done, then the first law of thermodynamics would say the change in internal energy is just heat added. So that makes sense why heat being added is a positive quantity, because you would expect the internal energy to go up. If you then considered a case where no heat was added or taken away, if you actually saw that the gas just spontaneously was put in a piston, and then the piston, the gas expand, pushing up the piston, that means the gas is actually doing work on the environment. And that would be a positive quantity of work following a negative sign. So that would give you a decrease in internal energy. And I think you would expect that if a hot gas was put in a piston at a fixed volume, and then you let the volume not be fixed, the gas would actually push the piston up and cool down while that's happening. So that's also consistent with that negative W if no heat flows. Okay. So hopefully that all makes sense to you. Anybody have any questions on that? Okay, so I'm going to just remind you that these not state variables. Another way you can think about it too is things that have a differential are things like, let's say, df of x, y, z, technically speaking, would be the partial derivative of f with respect to x times, wrong symbol, times dx plus the partial derivative of f with respect to y times dy plus the partial derivative of f with respect to z times dz. And again, if you think about it that way, it doesn't make any sense to think of Q as a function. You can't think of Q, the heat added to or taken away from a substance. You can't think of that as a function that has, variables N, M, volume, time, pressure, or excuse me, temperature or pressure, that kind of thing. This is also the origins of the exact differential equation, which is pretty much something you'll study maybe a quarter to a halfway into your differential equations class. And what they do is you'll see like they won't have the left-hand side, the df, that won't be there at all, but you'll see like some function times dx plus some other function times dy. And what you'll do is you'll take the derivative that's in front of the dx, you'll take the derivative of that with respect to y, and then you take the function in front of the dy and you take the derivative of it with respect to x. And if it truly is an exact differential, then you'll get the same answer for those two, because the order of the derivatives is irrelevant. So the function that was in front of the dx was supposed to be the derivative with respect to x. So when you took a derivative with respect to y, you're just taking the second derivative, one with respect to x and one with respect to y. And then when you do the one in front of the dy, that was supposed to be the derivative with respect to y. So when you take a derivative of it with respect to x, that means you've now taken the derivative with respect to x and y again. So if those two are equal, it's an exact differential equation, and then there's an easy way to solve it. But if that doesn't work, you either have to find an integrating factor or something like that. But in this case, you just wouldn't find such a function. You wouldn't be able to find anything that can be differentiated or anything. So any questions on that? So let's imagine, so here's an example. This is supposed to be a really simple example. Let's say 3,200 joules of heat is added to a sample. Okay, I'm gonna try to write the word sample again. I'm gonna erase everything. To, dang it, a sample of gas, and the gas is compressed by the atmosphere doing 1,500 joules of work on it. What is the change in internal energy of the gas? So you can imagine the gas being like in a little piston if you want. And what we're trying to do is we're going to say, okay, evidently I've got like a little lighter sitting under the metal piston, and I'm heating it up, and I'm keeping track of how much heat's flowing into it. And that heat is ultimately 3,200 joules. And then what I notice is, despite that, which would normally make the piston expand, despite that, the atmosphere is pushing down on the piston head, or excuse me, the piston, the plunger part of the piston, and pushing it down. And by calculating, I figure out that it's actually did 1,500 joules of work. So what I want to know is, what's the change in internal energy? So the solution to this is going to involve a couple of equations. Well, actually, it's only going to involve one equation, and that equation is delta E internal is equal to Q minus W. But really what's most important is you got to understand what Q is, what W is, and what their signs are. So I did say heat is added right here. So what I know is Q is equal to positive 3,200 joules. And it is said that work is done on the sample. So I can say W is negative 1,500 joules. That's the main part. That's the whole kit and caboodle that makes this even remotely difficult, is figuring out what the signs of Q and W are. So now I can just say delta E internal is equal to 3,200 joules minus negative 1,500 joules. And of course, that's minus a minus becomes plus a positive. So that's 4,700 joules is the change in internal energy. Again, if you think about the ideal gas as a model, that would suggest that the gas would heat up. But hopefully that makes perfect sense to you. And not only that, that it makes perfect sense to you that adding the heat alone causes the temperature to go up, but also an additional amount that the internal energy is going to go up. It's going to come from the work being done, because clearly you're pushing down this piston. That's going to cause the molecules to bounce off the piston faster, and ultimately that'll equilibrate down to the net kinetic energy of the atoms or molecules becoming higher. So that's equivalent to being a higher temperature, and that's equivalent to a higher internal energy. So you should think that both the Q and the W went into increasing the internal energy, which is what that minus a minus confirms for us. So does anybody have any questions on that? All right. Well, I don't see anybody doing anything to chat or anything like that, so it seems like you're getting it. You can, by the way, add to the internal energy, or excuse me, to the first law of thermodynamics. As I've told you before, the first law of thermodynamics is really just a statement about conservation of energy. And what it says is the internal energy is equal to the heat added to the system minus the work done by the system. But guess what? You can also add internal energy to the system by changing the kinetic energy. So if you really want a extended version of the first law of thermodynamics, what you could say is delta K, meaning delta kinetic energy, plus delta U, meaning change in internal energy, plus delta E internal, that's equal to Q minus W. So this is a general first law. Okay, so that's just extending it to include mechanical energy instead of just what we refer to as heat energy and work energy. So we don't do too much with that. Your book does a problem where you talk about shooting a bullet through a tree, and the bullet comes in with like 400 joules of kinetic energy, and it gives you a mass and or actually 400 meters per second, and it gives you a mass for the bullet, and then the bullet comes out of the other side of the tree, moving at 200 meters per second, again with the same mass. So what you're actually saying is, okay, that sort of changed the internal energy, because you can imagine the tree got a little heated from that. So you can just say that change in kinetic energy, which would be final minus initial, that'd be 1/2 times I think it was a 3 gram mass. So 1/2 of parenthesis 0.003 kilograms, close parenthesis, times 200 meters per second, close parenthesis squared, minus 1/2 of parentheses 0.003 kilograms, close parenthesis, times 400 meters per second quantity squared, plus delta E internal is equal to 0. So you can see from that delta E internal is going to change by the amount that the kinetic energy did. So that's an example that your book used. And I just wanted you to understand that the first law of thermodynamics is, in fact, just a restatement of conservation of energy. And I will remind you that really in post 1905, since Einstein introduced his special theory of relativity, that it's not really any longer considered conservation of energy, and it's not considered conservation of mass, but in principle, it's actually conservation of mass hyphen energy. So what Einstein showed through E equals mc squared is that every bit of energy that's created comes from some kind of change in mass. So as long as you keep track of the mass and the energy, everything's golden. In most cases, you can't really consider the change in mass, because if you look at E equals mc squared and you try to solve for the m, you get the energy, which, you know, even in the most severe cases, like that water being heated up by or being cooled down by the ice, maybe you get millions of joules. But guess what? If you take millions of joules and divide it by the square of the speed of light, a speed of light is 300 million meters per second. And then you square that, that's going to be basically 9 times 10 to the 16. So you see the mass is going to be like 10 to the negative 10th. So it's like out at 10 decimal places. So it's really unlikely that you have to worry about it in everyday life. So other than knowing that that's a general rule, don't worry about it. You can still call it conservation of energy. Any questions on that? All right, so a big part of the thermodynamics, which is what we're studying here, and chapter 20 is the last of it, chapter 19 being the next to the last, we're all setting us up to some extent to understand the second law of thermodynamics, which has a bunch of different forms. We're probably going to cover, in fact, these second law of thermodynamics, or chapter 20, in like a day, maybe even half of a class. But really what the second law of thermodynamics says, at least in one form, is spontaneously heat flows from a hot object to a cold object. That doesn't mean heat can't flow from a cold object to a hot object. It just means that it's not going to do so on its own. You have to put some work into the system, and there's going to be some waste and stuff like that. Another version, though, is that there's no engine more efficient than a engine that is done in a very slow type process. So they'd say a reversible process. So if you could do something in a reversible process, whatever heat engine that is, that's going to be the most efficient heat engine operating between two temperatures. So another version of the second law of thermodynamics is no heat engine can be more efficient than a reversible heat engine. And we're working up to being able to calculate the efficiency of a Carnot engine, which is one type of a reversible heat engine. So that's really what we're going for, is understanding the first and second law of thermodynamics. But to do that, we need some processes. So there's a whole branch of thermodynamics that, or a whole branch of physics called thermodynamics that you can't understand until you learn a bunch of definitions. So that's sort of what we're doing here, is we're going to go through definitions, and specifically the definitions are, let's begin with isothermal. You can probably guess what that means. Isothermal means the change in temperature of the system is equal to 0. So I'll keep using words like system. So you can just imagine that as a sample of gas or a sample of liquid with ice in it, maybe inside of a calorimeter, so that you can keep track and make sure no ice, no heat flows out of the system, stuff like that. That's another condition, by the way. So with the isothermal process, that means that the temperature does not change, and therefore a monatomic ideal gas would say that delta E internal is equal to 0. And that's because remember, the internal energy of an ideal gas was 3/2 nRT or 3/2 big N KT. So it only depended on temperature. So if the temperature doesn't change, the internal energy doesn't change. So that means that Q is equal to W from the first law of thermodynamics. Because remember, the first law of thermodynamics was delta E internal equals Q minus W. But if the delta E is 0, you get 0 equals Q minus W. So you can pull the W to the other side. And what they're saying is any work put into the system will basically become heat, or any heat put into the system will become work. So that's another way of looking at it. Any questions on that? So that's one process that's called isothermal. And the way you do that is either you carry the process out really fast, because remember what changing temperature means. It's not just the molecules of the hotter body hitting the molecules of the colder body and speeding the molecules of the colder body up, because that makes them in a very non-random way speeded up. But you have to wait for some period of time for those molecules that have been hit by the higher kinetic energy molecules. Those first molecules that were hit have to go in and collide with all the other molecules until all the other molecules, or all the molecules total, have a average kinetic energy that's not like bimodal or trimodal or three-modal or whatever, trimodal, quadrimodal, any of that kind of stuff. So changing temperature really takes a little bit of time. So a process like gas exploding inside of a piston and cylinder, inside of a cylinder pushing a piston, that's a very fast process. And in fact, we can treat it as if it's isothermal, because very little heat can really, or very little temperature can change. Obviously, it's hot from the explosion, but once that heat is there, it's going to be that temperature and it doesn't change. So that's one example. Another example is if you have the object in contact with what we call a heat reservoir or a heat sink or something like that. So that's an object of fixed temperature that no matter what amount of heat you put into it or take out of it, it doesn't change temperature. A good example of that is the Earth. The Earth is a heat sink. And for instance, a lot of houses nowadays are being built on concrete slabs because that puts them in contact with the Earth specifically. And the Earth can absorb a lot of heat from the house, or the house can absorb a lot of heat from the Earth and not change the temperature of the Earth. So that's what we mean by isothermal processes. And by the way, an isothermal process, just so you'll know, your book takes time to graph this, so I'm going to do it as well, just to remind you what the real pressure versus volume diagrams look like. So if we talk about pressure versus volume, pressure on the vertical axis, basically a graph for an isotherm would look like this. So this is isotherm for temperature T1. And then you can come back and say, well, here's another isotherm. And that's for a temperature T2. And in fact, what we find is that T1 is actually greater than T2. And you can tell that just by thinking about, for the ideal gas law, PV equals nRT. If you look at pressure, pressure would equal nRT over V. So the higher pressure would come from the higher temperature. So that's what we're trying to show you there. And that's why one is above the other. Now, another process we have to think about is one called adiabatic. And hopefully, like I said, if you've had chemistry before, you probably are somewhat familiar with all of these terms. But we're trying to put them in a very specific light because we want to use them to, again, derive expressions for the heat added to a Carnot engine and the heat expelled from a Carnot engine and adiabatic and isothermal processes. So we're just trying to figure that out. So for an adiabatic process, what that means is Q is equal to 0. So your system is isolated. So calorimetry is an example, for instance, of an adiabatic process. You're expecting that because you made this calorimeter cup, which has like an insulated air gap between the two surfaces, and very little conduction can go on, and all that's left is a little bit of radiation that even defeated convection. In that type of scenario, then the heat that comes out of, say, the warm liquid goes directly into the cold ice, and there's very little, if not zero, loss. So if it truly is 0, it's adiabatic, or if it's very close to 0, it's very close to adiabatic. So with adiabatic being 0, adiabatic meaning that Q is 0, that gives us that delta E internal is equal to the negative of the work done. So that's another interesting process. Plus, you can, in fact, take and look at a P versus V diagram again for adiabatic versus isothermal. And again, this is V here, and this is P here. And when you do an adiabatic versus an isotherm, let's say you're starting those off from different initial temperatures, then what you get, or excuse me, starting them off from the same temperature, what you have up here is, let's say, a particular volume, let's call it V1, and a particular pressure P1. The isotherm will go down like this. So evidently in this case, they both had, actually I did that badly. In this case, they both had the same temperature initially. And we'll call that temperature T1. Okay. But the adiabatic process allowed the temperature to change significantly. And this one right here is an adiabatic process. So you should think about that a little bit and try to figure out exactly. I'm not going to tip my hand on this. You can do enough of the conceptual questions in the practice test that covers chapter 19 so you get a feel for what the actual answer is. But do think, and you can use an ideal gas as a model, but do try to think to yourself, why is the isotherm higher at, say, volume V2 than the adiabat is? Okay. figuring that out and thinking about that with respect to the motion of the molecules for the kinetic theory and the molecular theory of matter or the atomic theory of matter is a really good, fruitful process. So I want you to think about that. But the main thing is, with that, we get all sorts of cool ramifications, because you'll see later that there turns out to be an ideal gas law version. P1 V1 to the gamma is equal to P2 V2 to the gamma, where gamma is defined to be Cp over Cv, which is the specific heat at constant pressure is the Cp, and the specific heat at constant volume is the Cv. And hopefully I have them in the right order. I do believe it's Cp over Cv, but you'll see that a little bit later. I'm just remembering off the top of my head. So this is one of the ramifications for an ideal gas. That's going to come in handy. And your book derives it. I won't take any time to derive it. I'm just going to work problems with it, that sort of thing. So now we've done two of the processes. There's also an isobaric process. So anybody think they know what an isobaric or isobaric process is? Anyone?
Is it where the pressure stays the same?
Exactly. Hopefully you can remember that, because one of the units of pressure is the bar. So that's where that comes in. So isobaric means delta P is equal to 0. So with that in mind, there happens to be this neat little expression that we use, especially when we're dealing with gases. Specifically, work is equal to the integral of P dV. In the case of P being a constant, this implies this delta P equals 0 implies that work is equal to P times delta V, which means delta E internal is equal to Q minus P delta V. So that's another ramification that might come in handy for us. So that's what an isobaric process is. There's also one called isochoric, or excuse me, isovolumetric. For some reason, my mind is telling me that isochoric is another word for it. I know isochoric's a word. I know isochoric's a process. I didn't see it in this book, and I can't remember where I learned it, but I know I could Google it. If I remember correctly, I think isochoric was the same thing as isovolumetric, but I might be wrong. It might have been adiabatic, but either way, isovolumetric, I think y'all can tell that that is pretty obvious what we're talking about there. In fact, it's delta V is equal to 0. And given that work equals P dV, that implies that work has got to equal 0. So you end up getting delta E internal is just equal to Q. So these are all big, important ramifications for these processes. And that's partly why they're trying to teach it to you, so you'll know what these processes are, and it gives you a chance to sort of study all the things that can happen with samples of gas and stuff like that. So when you get to section 19.7.4, they talk about work done with volumes. They derive that expression, work equals PdV. They even work it for the special case where the pressure is not constant. So for instance, if you talk about an isothermal process, which is right up here, that's another thing that can happen. So let's do, I'm going to make it obvious since I didn't put it up there with isothermal. So let's look at isothermal. Again. So work is equal to the integral of P dV. If we take an ideal gas, so we're going to say ideal gas, then we know PV equals nRT, and that means P is equal to nRT over V times dV. If it's isothermal, of course, that means N times R times T comes out in front, and I get the integral of dV over V, which is just nRT ln V2 over V1. So I know I wrote that in the margins. Let me write it down here again. It equals N times R times T times the natural log of V2 over V1, meaning the final volume divided by the initial volume. So that's another ramification. I just forgot to include it on isothermal, but I wanted to show you that. That's covered in 1974. You can also determine, for instance, since work equals the integral of PdV, this implies that, in fact, work equals the area under the curve. Okay. If you actually have a cyclic process, that's another type of process. And a cyclic process just means it starts with an initial condition, and then at the end, it's right back at that same initial condition. If that happens, you get something along the lines of this. Let's draw a graph again. And this is volume, and this is pressure. And you could actually have a process that goes from here to here. Maybe that's isothermal. And then from here to here, maybe that's adiabatic. And then it goes back here, and maybe that one's isothermal. And then it comes back to here. This is a cyclic process. And that implies delta E internal has to equal 0 because everything came back to the same value it had. So the pressure, the volume, and temperature are all the same at the beginning and the end. And for an ideal gas, the internal energy only depends on temperature. But for everything that we know of, the internal energy can depend on the temperature and maybe some of those other things, pressure, volume. But this is literally saying they're all equal. Well, when that's the case, then the work is the area under the curve or in the curve. So that's the work done during a cyclic process. So what I drew here was specifically the outlines of the Carnot engine cycle. Specifically, the Carnot engine does isotherm, adiabat, isotherm, adiabat, and that's going to be largely what we're focused on in chapter 20. But that's some of the issues that have to come to that you have to make sense of in chapter 19. The examples, like conceptual example 1911 and example 1912, are very straightforward examples. I think you can work them on your own. You can see them also in any of my lectures on my YouTube channel, so you can check that out. Same thing with 1913. I've given you all the details that you need for that. So these are just what we normally call plug and chug problems, meaning, hey, I've given you all these neat equations that you can use in the case of a cyclic process, or in the case of an isobaric or isothermal or adiabatic. You know what formulas are valid, and you just need to use those. So that's what all these examples 1911 through 1914 and all that stuff is. So you just want to keep doing that, making sure you follow these examples, and it shouldn't be very hard for you. Once you've done that, you're basically in a good spot. I don't think I need to show you those, but you're welcome to ask me any of them if you have any problems. We've only got about 5 minutes left. One thing we got to talk about is a free expansion. So in a free expansion, what you can imagine is, I'm going to change this color from green back to my blue that I like. So another example is free expansion. So what we're talking about here is ideally it would be like an outer space where space is essentially a vacuum. Okay. Or here in the lab, you can sort of make a container that has a gas in it and put a little stopcock on it. And then on the other side of the stopcock is another container that you've sucked all the air out of. So it is close to a vacuum as we can possibly get, probably about as close as we can get in outer space. If you do that, then the free expansion is just when you open that stopcock and allow the gas to flow freely into the other container. So we'll say this is our little stopcock valve like this, and this is our container right here. And in fact, it's going to be a thick-walled container, so it can isolate the system. It might be an adiabatic system, for instance, because it's not letting any heat flow, all sorts of good stuff. But the main thing is you initially have all these molecules of gas in here on this side and nothing into there. And then when you open the stopcock, the other side fills up. That's what a free expansion is. And a free expansion, it can't be plotted on a PV diagram, because really to make a PV diagram, you're having an equilibrium between pressure, volume, temperature, and all that stuff all at one time, meaning an equilibrium state where you can define what the pressure is specifically, right? And if you have too much variation, then obviously that would be a problem. Or if you have too much variation in temperature, that would be a problem. So if you have like, the molecules all next to the hot wall, all those molecules have this really huge kinetic energy, and all the molecules to the left of those have entirely different but very consistent average kinetic energy between each of them. That's not an equilibrium state. You have to wait till you can actually find a like bimodal, trimodal, quadrimodal distribution, and then it's sort of equilibrium. So that's a way of thinking about equilibrium. But the main thing here is, since this is a vacuum, we have P is equal to 0 in here. And then the expansion is going to have, the expansion is going to have Q equals 0 and work equals 0, because the pressure is 0. And because of that, that would suggest that the delta E internal is probably going to be very close to 0, if not 0. We know for an ideal monatomic gas, it'd be exactly 0. But in this case, it's not necessarily going to be 0. So for an ideal gas, okay, so that's a free expansion. When we actually do this experiment, we get a very small change in temperature, but we haven't been able to make it exactly 0 in reality. So that's another process that goes through. What I want to do now is, now that I've covered all these sort of processes, I want to give you an idea of what's going on. So we're going to do a molar specific heat. So it still says specific. So it's a heat that is, in this case, not per mass, per gram, or per kilogram, it's per mole. So for instance, we'll use C, which could have units, for instance, of kilocalories per kilogram, or excuse me, not per kilogram. Okay, evidently I can't erase that too well. So it'd be kilograms per mole Celsius degree or something like that. And specifically, we have a, in the capital case, it's got to be per mole. So if it's a capital letter, like it is there, that means per mole, whereas the lowercase c would mean like kilocalories per kilogram Celsius degree. Okay. Now, when you're talking about a gas, there is a difference between CP, meaning specific heat, for delta P equals 0, meaning at constant pressure, and CV, specific heat. Whoa, there's too many letters on that one. Actually, probably easier to erase it. So specific heat for delta V equals 0. So this one, notice, would imply work equals 0. So all the heat's going straight into all Q raises T. Whereas this one, you can actually have some of the heat that you add to it going into work, and some of it can add into going into temperature. So in this case, heat goes into delta T and W. So if your goal is just to change the temperature, then you'd expect C at constant volume to be smaller than the C at constant pressure, because at constant pressure, the heat is not only changing the temperature, it's also doing work, whereas at constant volume, it's just changing the temperature. So it turns out that if you use units of calories per mole Kelvin, then CP minus CV is very, very close to 1.99 / 2.00 calories per mole Kelvin. Okay. And that happens to be what you might recognize is related to R. Notice it has the same units of R. And in fact, the model suggests that CP minus CV is equal to R, and that CV is equal to 3/2 R. Therefore, CP has got to be 5/2 R, if I remember correctly. Hopefully I'm remembering that correctly. And then finally, as I said before, we also define the quantity gamma, which is defined to be CP over CV. Okay. So those are all expressions you can use. You're free to do that. We've now went beyond slightly by about 2 minutes the end of class. So you guys are, of course, free to go. We'll finish up this chapter, which will cover adiabatic expansion, heat transfer, conduction, convection, radiation. And that'll be pretty much it. We'll do that next time. But you really have everything. If you just read the chapter to get the last sections, or you look at my videos, you got more than enough information to do all the chapter 19 homework. So again, I still set the date back, so we're still going to touch on it come Tuesday. But you guys are free to go, and I'll wait for the last person to leave in case anybody has any questions.
Professor, I did have one question.
Okay.
Not really like a question so much as like an observation.
Mhm.
I noticed like last semester and this semester, like when doing the homeworks, that the homework one like does a much better job of like teaching concepts and stuff than
Right.
like the conceptual does.
Right.
So I was just like, so for chapter 19, we have homework part 1, and then homework part 2 is due at a later date than part 1. But the conceptual, I usually find it like way like better going into the conceptual after doing the homework
Oh, gotcha.
for a chapter.
Gotcha.
And it, like it's a shorter assignment, and like I mean I can go in there and do it beforehand. I just didn't know if like
Yeah, it might actually be better for me to have the conceptual questions due on the last homework date. Yeah, I'll do that. And I think your argument's correct. You some of the conceptual questions you can get immediately from the reading or from my lectures, but some of them you really don't get it until you solve the problem. So yeah, I agree with that. I'll start changing that. I want to let you guys know too, by the way, that the MATLAB and Mastering actually put all the homeworks in and made them available. So you might, since we've gotten a little bit behind what my original schedule is, you might actually be seeing like chapters we haven't even covered coming up on their due date. Remember, and I said this in my syllabus, if it's a chapter we haven't touched yet, then I don't care what the due date is, it's not right. So don't worry about that. So far, we've only done 17, 18, and 19. So only those homeworks should be coming due anytime soon. And even 19, I still have an extension on that. So once we do chapter 20, then chapter 20 will come into play. But just keep that in mind. But yeah, I'll do that for the future ones. I'll go ahead and make the conceptual questions due on the last day. So there really won't be a difference necessarily. It'll just be that the conceptual questions won't be due until at least the same day as the last regular homework. They are important. So keep that in mind. That's part of the reason why the conceptual questions appear in the practice test, because I try to do some conceptual questions in all the tests in general. I don't necessarily do them at the final exam, but all the other tests I do. Anything else? Anyone else?
Yes, so can you go back to previous page, please? Yes, thank you.
No problem.
Well, thank you, Professor. Have a good one.
You're welcome. Thanks, Taylor. Appreciate your advice. Various or Tony? Nope, they're gone. Sang, do you have any more questions, sir?
No, I'm just writing down the last equation. So
Okay, no problem.
all right, thank you.
All right, have a good one.
You too.
Bye-bye. Bye-bye.